I actually reset this up?
Because right.
Ah.
Okay, thank you. I would like to thank the organizers for all the hard work they obviously did to organize this meeting. So my talk is about the variational, about energy conservation and how to get it from variational methods. And so I'm at École Polytechnique near Paris, and this was supported by PSL. And I'd like to thank John Thuber and also Anwood Gassman for stimulating and inspiring discussions and problems. Okay, so energy conservation goes back a long time ago, starting maybe from Arakawa down to, say, Anwood Gassman. It handles non-divergent flows, shallow water, rotating shallow water flows, three-dimensional hydrostatic flows, and three-dimensional non-hydrostatic flows. So I will focus a bit, not handle all of this. First, I will focus on energy conservation on C-grid in rotating shallow water equations, and I'll talk about all that work and find a common pattern. And in the second part, I address the three-dimensional flow and how to get conservation of energy there. And obviously, the first part I talk about how to get energy conservation on these kind of grids. And as John said, one motivation to get it here is to have a good balance of mass and velocity degrees of freedom. And then you have to overcome the non-orthogonality of this pair of dual grids. Okay. So first I explain how you can get energy conservation of that kind of grid, and how you construct the non-diagonal Hodge-star operation John talked about, and make a connection to the discrete Poisson-Braquet approach, which was followed by Anwood Gassman for her non-hydrostatic model. And then I revisit previous schemes with this in mind, and make also the connection with the Poisson-Braquet approach. And then extend this to primitive equations in a general vertical coordinate, not Eulerian coordinates. Okay, so we are on a C-grid, so that means that we have made a choice to describe a vector field. We could have cell average components or pointwise, but the preferred way and most natural way on a C-grid unstructured mesh is to describe velocities either as integral along those curves or integrals across surfaces, that is fluxes. And if you're orthogonal, you can more or less pretend that they are the same thing, but you cannot when they are not orthogonal. So you make the distinction, and to make your best budget, you need to compute your fluxes across the primal faces, knowing the circulations along the dual edges. So these are your data, and this is what you want to know. And you want to do that at least consistently and while conserving energy. So I'll start with the linear wave equation, pressure. So that's the mass budget. Pressure is the same thing as mass. Velocity budget. So my degrees of freedom are the cell averaged mass, edge integrated velocity, and as that's what John explained before. This is my Hodge-star, which converts edge integrated velocities to fluxes. Then I take the divergence, which is just an incidence matrix, just differences. And the same thing for velocity. I divide by the area to get a pointwise value, and I take the difference between the endpoints to get the edge integrated circulation. Now I want to conserve this energy, so that's potential energy, that's kinetic energy. And well, let's see what happens in time to energy. So I differentiate, and I find this kind of thing. And if H is symmetric, everything will cancel, and I will get 0. So the only serious constraint is that the interpolation operator should be symmetric, and that's not so easy, but there's a general way to derive a symmetric operator. It's just to form a symmetric quadratic form. So that's kinetic energy, and that's actually what Perot and co-authors did earlier. I can't find the date anymore. So we will construct kinetic energy based on the degrees of freedom we have. We will define the flux as the derivative of kinetic energy with respect to these circulations, and by its function find the primal mesh. So this step can fail. And the construction I propose is to, whoops, here, here. So at each corner here I have two data, so I have enough information to reconstruct a full vector. So I do that reconstruction at each corner. I square, I weight by the area here, and I get my kinetic energy on that cell, and then I sum up over all cells and I get my total kinetic energy, right? So, and there are some geometrical happy accidents which happen, so that when I differentiate this with respect to the circulations, this actually gives the fluxes across these lines, provided these points here. So the primal vertices are the barycenters of the dual cells. So there is some amount of luck going on, but it works. And I can prove that it's exact for uniform flow, so it's a consistent interpolation. Okay, so that's we have been a bit lucky. So let's try if we can rely on something more systematic, and that's where the Poisson bracket comes along. So here, what we have been doing is we want to conserve this energy, and we have defined the flux, which is here, the mass flux, as the derivative of energy with respect to velocity. And actually, if you look back at the previous equations here, before, the tendency of pressure is also related to the derivative of energy. No, sorry, the tendency of velocity is related to the derivative of energy with respect to pressure, right? So we have this nice pattern, and that's how everything cancels out to give that energy is conserved in the end. So that's actually a discrete, this here is an antisymmetric expression in the derivatives of the energy and of any function of pressure and velocity you want to find the evolution of. So that's a discrete Poisson bracket which has a correspondence in the continuum. You can write these wave equations exactly the same way. So the mass flux is the functional derivative of energy with respect to velocity, and the pressure is the functional derivative of energy with respect to pressure. So we have actually involuntarily mimicked this Poisson bracket structure of the wave equation and obtained the conservation of energy. So antisymmetric guarantees conservation of energy, but we don't try to achieve this much more demanding property of the continuous Poisson brackets. Okay, so that's a much more systematic way to get conservation of energy. So does that work with the shallow water equations, and was that actually used before? So for the shallow water equations, we have a Coriolis force. So for this, we will introduce the entrainment velocity, which is rotation rate cross position, absolute velocity. The curl of entrainment velocity is the Coriolis parameter. So the curl of absolute velocity divided by h is potential vorticity. The energy is like this, so that's kinetic energy times h, and that's potential energy. Here I'm averaging in, say, on the plane, on the f plane. And so the functional derivative of the Hamiltonian with respect to absolute velocity is the mass flux, And this is, with respect to height, it's the Bernoulli function, both of which appear in the vector invariant form of the equations, which is well known and has been used for a long time to derive, to discretize the Shell-Waller equations. So now, just using the chain rule of derivation, any function which depends on the height field and the absolute velocity field will evolve according to this. So basically, the green term results from that one, the blue term from that one. Now this one comes from this one, but I have done an integration by parts to obtain antisymmetry. So I need a discrete rule of integration by parts in my discrete scheme. So that's antisymmetric, and if f is h, then energy is conserved. That's 0. Okay, so that's the recipe. I will discretize in vector invariant form, as actually not everybody does, but many do. I approximate total energy, define mass flux and Bernoulli function as derivatives of total energy, ensure that div and grad are compatible, so that's my discrete integration by parts rule, and I'll make sure the Coriolis term is antisymmetric. So that's all. And you are guaranteed to have conservation of energy. So the question I ask now is, what that's actually done before? So we can go back in 1975, the original Saduni scheme on a C-grid, and the energy, so there are two variants, one conserves entropy, the other one conserves energy, so I focus on the energy conserving variant. So the energy goes like this, so potential energy. To compute kinetic energy, I have to square U and then average to the P points, the mass points, and then multiply by H, so that's an H here, and that's the two components. So that's the formula derived by Saduni, essentially by inspection, by demanding that energy is conserved, and you can actually find that that's exactly dH du and dH dv, and the Bernoulli function is exactly the derivative of H Hamiltonian with respect to H. So these are, now we are discrete, right? We're not in the continuum anymore. And if you can consider any function of H, U, and V just by the chain rule, you get this expression, which is antisymmetric in F and H. So it will vanish if F is equal to H. Right, and this is the antisymmetric Coriolis term. Now there was a variant of that scheme mentioned in the paper by Hollingsworth in 1993. So they actually use a slightly different Coriolis discretization, so I won't show that. But they wanted to conserve a different kinetic energy to control a numerical instability. So they changed this expression to that one, so with more averaging here. And they figured out the mass fluxes which would guarantee the conservation of energy, but actually it's simply the derivative of H with respect to U and V. So they had constructed a discrete Poisson bracket. Now Trisk. So Trisk is an unstructured grid, and I won't show the algebra for the Coriolis term. I'll show the energy terms. So my degrees of freedom, it's cell integrated mass and edge integrated velocity. That's my mass budget. So these are plus or minus 1. So that's my incidence matrix here. And that's the Coriolis term and gradient of the Bernoulli function. That is the expression for the energy. So here, that's the height, mass divided by area, squared, multiplied by g and by the area. So that's my potential energy. To obtain kinetic energy, so I take my circulation here, I divide by the length to get the normal component of velocity, then I square, I multiply by the reconstructed value of h here, and then I multiply by this, which is a kind of area of that kite shape volume. and I think it's 1/2 between 1. And so the way this is reconstructed is not really important. The weights sum up to 1. And if you just read the algebra, so the mass flux, it's the normal component times the length here multiplied by the reconstructed height, and it's exactly the derivative of h with respect to the circulation here. And same thing for the Bernoulli function, it's the derivative of the Hamiltonian with respect to the cell integrated mass. So actually the energy conserving tree scheme is a discrete Poisson bracket too. Now I have 3 minutes to generalize all these to 3D primitive equations in a general vertical coordinate. So at first I will write a variational principle in a general vertical coordinate and examine what it takes to have an energy conserving scheme. So that's my general vertical coordinate. So that's a surface eta equals constant. So I still have an entrainment velocity, and just for increasing the difficulty, I will have it depend on the vertical coordinate. So the curl is still 2 omega. In the standard case, this would be vertical in the shallow atmosphere approximation, but you can also tweak R so that this is actually an oblique Coriolis vector to have a full Coriolis force. But that's embedded in the z dependence of the entrainment velocity. And I define the absolute velocity as before, relative plus entrainment. Because I'm in a general vertical coordinate, I'll define a pseudo density, which is the physical density times the the variation of height with respect to the general coordinate. I define a mass-weighted entropy. In the sequel, all the gradients and divergence, they are taken along the model surfaces. And because, so if this is a Lagrangian vertical coordinate, then I don't have any mass exchange between model levels. But in the general case, I will have a mass flux through the interfaces, and I call it W. Now the energy corresponding to the hydrostatic equations, it goes like this. So that is relative velocity squared. So that's kinetic energy. I multiply by the pseudo density. This is internal energy. This is specific volume, so the inverse of rho. This is entropy. And that is the geopotential, which gives you the potential energy. Now I do my functional derivatives, and I find the mass flux, the temperature, and the Bernoulli function. And there is another relationship which will be useful later, which connects the various functional derivatives of the Hamiltonian, and which expresses that the Hamiltonian should not depend on your choice of the placement of the vertical levels. It's a Eulerian quantity. And now it's well known that the primitive equations, they have vector invariant form. So mass must evolve with a vertical mass balance, horizontal mass balance and vertical mass balance. Entropy, so that's mass-weighted entropy. I will have a divergence of a vertical flux, divergence of a horizontal flux. And so that's precisely mu u times s. And for velocity, written in a vector invariant form, I don't see the time anymore. Okay, 21. I also have vertical advection, generalized Coriolis term, gradient of Bernoulli function, and that's gradient of entropy times temperature. And because we are hydrostatic, we also have the hydrostatic constraint, which can be written as the functional derivative of h with respect to z equals to 0. So I can't give the details, but you can obtain them from the principle of least action. Now I want to ask how some function of all my variables evolves in time, and by the same kind of algebra as before. All these red terms come from the horizontal terms of the equations. So I find again a Poisson bracket, which is antisymmetric in H and F. So that's well known, in a sense. This comes from the hydrostatic constraint, so that will vanish for the Hamiltonian too. And that comes from the vertical transport. And I don't think anybody has written that before. And this also vanishes because of that being proportional to this, and this is 0 due to hydrostatic balance. Okay, so now if I want to conserve energy, well, I will need to make this antisymmetric. This will actually be an equation to find Z. Hydrostatic balance in primitive equation models is how you find the height of each layer. And then these blue terms, they will define the value of theta at intermediate layers if you want to conserve energy. So that's something Simmons and Burridge did in an ad hoc way in 1981. And you can also think of doing the same thing in a weak sense, in a Galerkin sense, and then you would define adequate functional spaces. The Poisson bracket would give you the weak form of the equations. And if you take the same space for z and vertical velocity, then this will be automatically enforced for the same reason as before, for that reason. So I think I have never actually written a scheme with that, but I think that would yield conservation of energy. Okay, so we have derived an energy-conserving Schauer scheme and a non-orthogonal C-grid, which actually can be interpreted as a discrete Poisson bracket, as actually schemes that were designed earlier. And I have extended this variational framework to three-dimensional equations in a general vertical coordinate. So this generalizes previous work. There are many more papers in that line of thought. I think it's important to mention that this suggests to prognose the absolute velocity or angular momentum in the spherical case. And I have mentioned several possible paths to energy conservation. So currently we are applying this to the deep atmosphere quasi-hydrostatic equations with variable gravity. There is a poster by Marine Thor on that. And one final remark. So in a sense, that shows that conserving energy is easy. Well, at least there's a systematic way to get it. So the hard work is to get the good linear properties like numerical modes, dispersion, geostrophic balance, and at the same time high order. So I hope we have talk solving these problems. Thank you. I'm sorry.
We have time for a couple questions.
So what's the order of your scheme? Is it
It's first order. It's probably first order. It's second order on regular grids, but on the sphere it will be first order.
And another question: do you rely on polygonal cells, or can you also have?
Okay, so I can handle only. So the trick works if the dual cells are triangles or quadrilaterals. I cannot handle an arbitrary mesh. Okay, so the dual cells here, they can be triangles or quadrilaterals. And that's because there are some happy accidents which occur here and which will not occur for instance, a pentagonal dual cell. But that's pretty general already. You can do many meshes with that.